Then, so Tilman is going to talk about the transport without charge. Please.
Okay, it's a great pleasure to be here. Thank you very much for the invitation. So I will talk about transport without charge, but with a focus on thermomechanical transport. But let me briefly have a look at maybe a little bit exotic here, this topic of cold atoms. So the cold atoms were, most of the cold atoms experiments were kind of done can be looked at as particles in a container. And in a way, we have achieved incredible sophistication how we can manipulate this container. We can change from fermions to bosons. We can cool them, we can change the interaction, add lattices and everything. But the question is, okay, why only one container? What about having a second container? But a second, that doesn't change much. It gets interesting when you couple these two containers, because then you can have particle transport, heat transport, or spin transport. And I should emphasize here that the research that I will not talk about, that Jean-Philippe and I did that together most of that research for quite a few years, and it was a great pleasure to do so. Let me show you the basic experimental setup. The starting point is a lithium Fermi gas, as we know it, an elongated one that's shown here. But we now shape the light potential, the potential such that we get two containers, and which are coupled by a channel, and that channel we can structure. And so that is shown here. This gives you a bit the sizes. And now let's run this little animation. Now you see there's a channel between two containers, and now additional beams are used to structure the channel. Here's a green beam, making it very narrow, for example, that you have single channels. And then there's an additional red beam, what we call gate beam, that changes the chemical potential in the region, in the channel region. And we will use exactly the control of this channel region and being able to have kind of a transport probability as a function of the number of channels as a function of energy that we will use. But I think the basic idea of the experiment is seen here. So how do we measure? We measure by creating an imbalance, some sort of imbalance. It can be a particle imbalance, or it can also be a temperature imbalance. And then we let it evolve the system. After a certain amount of time, we stop and watch what has happened. And then we measure, for example, the particle number from images. We extract particle number and the energy of the particles, and then we use equation of state to get chemical potential and so forth. And these are the typical idea of an exponential decay, as you could imagine. And I would like to point out there's a review about these, a recent review, again, together with Jean-Philippe, about these type of measurements. So let me start with to get you an idea of the system, the most extreme situation, that is if you have just a point contact, which is well known, of course, in mesoscopic physics. So if you have only a single channel, but here it is, you can look at it in terms of that you have quantized transport of neutral matter, not of charged matter. Okay, so we make a very narrow channel, and then you have just an imbalance of the atom numbers in the left and the right reservoir, and then you determine the conductance by such a decay measurements. And what you see as a function of, well, what I told you earlier, this red gate beam, where we can then open up the channel in the center. So here on the right-hand side, we have a very tight channel, so there is no current going through. And if we open up the channel, more and more conductance channels open up, and the conductance you expect to be 1/h. Well, in a 1D model, you can easily derive that your current should be chemical potential difference divided by h for a single channel. So your conductance per mode is here in the non-electronic case 1/h. Okay, so maybe to show you that these systems have a bit of a different character than electronic systems, and they can lead to surprises. And in particular, we saw a surprise when we changed interactions. So when we go from weak interactions to a strongly interacting Fermi gas. Well, in one limit, this strongly interacting Fermi gas is a superfluid. Okay, so what is happening? I mean, we can do that using Peschbach resonances, which so we have two spin states which change the interparticle interaction. So this is shown here. On the right-hand side, you see the Peschbach, the magnetic field, and then scattering lengths plotted. And on the left-hand side, you see the conductance, and there you see that the conductance plateau at 1/h. And now we increase the interactions, the attractive interactions. You could think of that the system starts wanting to pair, and then you see, but it's not yet superfluid. So what you see then is an increase in the conductance, so which is not in line which you would expect from a Fermi liquid, because there you would expect it would still be, well, 1/h per quasi-particle. And then most surprising is if you're above 2, because the other you could still explain by a pairing, a superfluid pairing. And then if you go even higher, we see well, plateaus or shoulders at up to 4, which puzzle a bit. And I think they were basically, and then at resonance, you see a strong conductance, which is kind of coupling two superfluids. So that caused a bit of thinking and questions. How can one explain? And there are basically two types of theories. One is more or less saying, okay, we have preformed pairs in the 2D channel, and these preformed pairs are injected in the channel. They act like bosons, and you get a higher conductance. The other is that you treat it in a way that you say, okay, I have a one-dimensional system. I expect the channel to be superconducting first. And if I have a superconducting region in the channel, then the question is, where does my channel entrance start, here or a bit later? And depending on where you put this, and if the superconducting wave function enters into the reservoirs, it can couple to additional modes, leading to a higher conductance. Okay, so that was just a bit to give you the flavor. And now I would like to come to thermoelectric or thermomechanical effects. That work was actually inspired in a collaboration with Antoine Georges and Charles Grenier and Corinna Collat. And for those who know the BEC conference, they will realize where that is. Thermoelectric effect in this community is, of course, I don't need to explain it. For me, it always, when I think of that, I get really humble, because if one could improve these type of effects, one would really make a big contribution to energy problems. There is one direction in this thermoelectric systems that is the nanostructuring of low-dimensional thermoelectric materials, and this spirit is a bit what we did in the recent experiments, where we kind of shape the energy density, the density of states inside the channel. Let me explain the basic idea of the experiment. And so what we do is we have the same atom number in both reservoirs, and then we heat up using a stirring laser beam. We heat up one of the reservoirs, and then we watch the atoms flow, and so the atom number in the two reservoirs and the temperature. And that's what we see. So what we see is that the temperature decays and goes to a medium temperature, and all the hotter gets colder, the colder gets hotter. But what we also see is a current of the atoms from the hot to the cold reservoir, and then a decay of it. So the basic idea, well, one can, in a very simple picture, well, one can look at it, and I mean, one should point out here that we are not obstructed by coupling to phonons and all these imperfections. So this is really almost a perfect system, as you can write down your potential, you can write down the atom-atom scattering, and you can, you know, the geometry of your system. In this here, a very simplified geometry, you have two reservoirs with each with 3 particles, and left obviously have more energy than the right, and then you have some coupling between them, and there you can see that, well, here the currents and this energy, they compensate, and this energy you have a current from right to left, and at this energy it's compensating, and here it's going again to the right, and overall you will first have a kind of a higher energy, a faster current to the right, and that gives results in this thermoelectric current or thermomechanical current. Okay, in general, one can see that the particle current is driven by a chemical potential and the heat current by a temperature difference, but of course they are also coupled, and that's the Seebeck effect or the Peltier effect. And in total, one can describe that by 3 constants: the thermal power of the channel, and then the conductance and the thermal conductance. Okay, so now what can we do in our experiment? So, and this is, well, the main view graph of what we do in the experiment, both kind of schematically from an experimental point of view, and then the energetics of the system. And then what we will do then is both look at these situations either with a close to non-interacting or a very weakly interacting gas, and then with a strongly interacting close to superfluid gas, or where superfluidity is in the center region achieved. Okay, so how should one look at it? So we start with the same atom number and in a given potential, and now we heat up, and that means here for the left-hand side that we lower the chemical potential and of course broaden the Fermi distribution. And on the right-hand side, well, we are at a fairly sharp Fermi distribution. We didn't do anything to that. And now we have two beams in the center, and these two beams, their function, well, one is repulsive, one attractive, but the main point of these beams, what they do is they open or close a number of channels in this region between the two reservoirs. So you could imagine here, for example, so these are three different situations here in the center. Okay, so here on the left, the green situation, which we say we have a gate beam, a repulsive gate beam. There you can see, for example, well, let's assume here's a particle at high energy that will be able to pass through on the other side, because the channel is above the energy to pass through the channel. Whilst, for example, a low energy particle here will not pass through, even though in the other reservoir it would find a hole. Okay, and now we can change from the green situation, say, to the gray situation, and there we can see, okay, now also the holes can be filled by particles flowing from right to left, and not only the high energies from left to right. And then we can go to even more extreme situations by lowering this potential, and then you can see that, okay, maybe we get to a certain stage where even more particles will flow from the right to left, because here are so many holes. Okay, so that is the situation, and between those different situations we can change, and we can change the interaction. Okay, so what do we see in the experiment? Maybe I'll start here with the lowest view graph. That was where only high energy particles can pass through. We see that slowly the temperature will equalize. And then we also see a strong particle response, a particle flow, and that will be a flow from hot to cold, and then it will go equilibrate over time. And when we open up the channel, kind of lower the gate potential, then we see that we get faster and faster equilibration, and the particle imbalance response get weaker because it more is compensating. And we also see that here, that's the blue curve. There is a curve where we only see temperature equilibration, that only the temperature equilibrates, but there's no particle current. Well, there are, of course, particles flowing, but the particles flowing from left to right and right to left, this current is balancing. And so now we can in a way, so there is no thermal current between the two reservoirs, and here we have a strong thermoelectric current. One can now, of course, wonder why not looking at that as strong interactions. And here I want to bring a little quote from Vitaly Ginzburg. I found that in the thesis of Dominic Husmann. So, and he inspired us, of course. And he says, I've been working in physics. Oh, I have to speed up. So anyway, I've been working in physics for 50 years. Ginzburg said, not me. But I continue to be surprised by the role of fashion in scientific research. Attention to or neglect of many problems is difficult to explain. Here, sometimes important roles are played by mysterious forces similar to the forces which dictate fashion. In any case, I still cannot understand why thermoelectricity, electric phenomena in superconductors, is neglected. Merely referring to experimental difficulties is not enough. Okay, so we address that issue by changing to a strongly interacting system. And what we see here now is again the same type of curve. So here the particle response, here the thermal response, again for different channel depths. And we see now that for a deep channel, we can reverse the thermoelectric current. So in that case, there will be a current from low, from cold to hot. So we can, in a single device, the direction of the thermal current. To our knowledge, I mean, individually, both directions have been shown, but in a single device, I think that is novel. Okay, and here one can compare it. One can now be quantitative and also measure the thermal power of the channel, and the current that we observe that has two contributions in the thermal power. The one is a channel contribution, that was this energy dependence, and the reservoir contribution, which has a different sign. And from our measurements, we can write down a little linear model, and then we can determine our different coefficients of the system. And then we can also look at the entropy current, which has a reversible term, and then there, of course, one can imagine that if I have a superconducting system or a strongly paired system with the particles, I will bring much less spin fluctuations due to the correlations in the system. And we can now measure quantitatively the thermal power. And here we see the blue data, that's the data for the non-interacting, that levels at the alpha of the reservoir. That's exactly where then we get zero current. And here the orange data that goes well below alpha of the reservoir, and we can reverse the current. We can also measure the Lorentz number, which one would expect to follow, for a Fermi liquid, you would expect it to follow the Wiedemann-Franz law. I mean, it describes the ability compares the ability of the system to conduct heat and particles. And here we see that the Lorentz number for non-interacting, that's the expected one for kind of a Fermi liquid, that's this solid line. For non-interacting, we measure somewhat above, but we have there low current, so we have fairly big error bars, so we are a bit above. We have much larger currents, can measure much better for the in the superfluid region, and there we see very low Lorentz numbers, as you would expect for superfluid. Okay, so let's skip because the time is at the end.
Can you
the situations, but that we will skip, and I will also skip about on the spin-dependent currents that one can use, but I will not skip about the thank you page. And here I would like to thank the Lithium team, which have made all this work possible. So that's our team.
Okay, so thanks, and thanks for speaking up to stay almost on time. So we have now some time for questions. So please, Asa.
I have a question about this manipulation of the junction to reverse the thermal current, the thermoelectric effect. Is that essentially changing the particle hole symmetry?
Yes, it's playing, and it's kind of you see you couple those the energy channels, and which energies do you couple on both sides? That's what you play with.
I see.
And that we can adjust and modify. And the limitation, there's a certain limitation, because in principle for non-interacting, we would have also expected to see a reversal, but there we could just go to the limit where it compensates, so that we have zero current, and we guess that we get losses. I mean, we have weak interactions, but that we get losses because then our potential lines are too wiggly. And that's what we guessed that the reason was. So that's why it only worked the reversal with the superconducting that it worked.
I see. Okay, thank you.
Thanks. Another question, Leonid?
Hi.
Hi, Tilman. Good to see you in Santa Barbara. Yeah, thanks. It's a wonderful talk, and again, revives the things that we discussed a while. So, but can I ask you again? So this Lorentz number, right? So when you take the ratio of the thermal conductance to the particle conductance, and I appreciate that qualitatively it's great that you have a much smaller ratio in a superfluid state. But I didn't follow your latest work. So is there a way to independently measure the denominator, the G, in the purportedly superfluid state? The thing that I maybe putting in a broader context, you see, if I chemical potential bias the superfluid junction, then in principle there is a Josephson AC current, and then there is some dissipation which is interesting to investigate. It's also a good theoretical question, but my question experimentally, pragmatically, so this G as a dissipative conductance through a superfluid channel, was it measured as an independent quantity?
I mean, we can measure. I mean, we can measure the initial current that we get, but
right.
It's well, from that we did use our G.
So basically, G is deduced from the extrapolation of the initial decay of the. Okay,
yes.
Right. So that's basically the same as it was done in a couple of years. Okay, yeah. Thank you. That's very helpful. Thank you.
Thanks. Any other question? I see. Okay. Asa, you have an other question, or it's probably the silly old one?
I just forgot to.
Yes. Okay. So if not, okay, it's one last chance. Then first let's thank Tilman and the other speakers of this session, morning, afternoon, for wherever you are. And I think yes, now we have a break, and then we should reconvene in 1 hour according to the program. So thanks a lot, and see you later.
Okay.